related to the uncontrolled rectifier. Okay. So here first we will take this. Here you can see this circuit shown below is initially relaxed with the switch closed at t is equal to 0. The conduction time of the diode is around. What is the value you have to see? So here you can see this. It is like a RLC series circuit. Here you are having the diode. So when the RLC series circuit, in this we are having the energy storage elements. So when it is fully charged, then the current flowing through this element will be 0. Okay. When the capacitor voltage is maximum, the current will be 0. Okay. So here you can calculate this by using this expression. So in this I of t is equal to Vs by omega L e power epsilon r t sin omega r. So this current should go to 0. For this sine term, when this sine term is equal to 0, then the current will be 0. Okay. So sin omega t should be 0. So that omega t should be pi. Then only sin omega t is equal to 0. Okay. So when this omega r t is equal to pi, then the current will be 0. So first we have to know the value of omega r, then only you can find the value of t. So to find the value of omega r, we are having the expression omega r is equal to square root of 1 by LC minus r by 2L the whole square. This expression already you know. So in this you have to substitute the values of RLC values. So here it is 10 by 50. That is we are having this values here in this diagram they are given. That is 5 microfarads. That is the value of the capacitor, and 10 ohms is the resistance value, and 1 millihenry is the inductance value. So we are using this values in this expression. So then finally you will have here 132.28. That is 13,228.76 radian per second. Okay. So the diode will stop conducting when omega t is equal to pi. So we are using this value, omega r value in this expression and finding the value of t1. It is equal to pi by omega r. It is pi by this value. So finally you will have 237 microseconds. 237 microseconds. So here the answer is B. Okay. The answer is B. It is 237 microseconds. Next, we'll go to the second question. So here, the effect of using freewheeling diode, or what is the effect of using the freewheeling diode? We already know that it is providing the continuous load current and increasing the frequency, and it will not allow the flow of negative voltage, application of negative voltage in the load. Like this, we are having various things. Okay. In this, here they are given some options. That is, the effect of using freewheeling diode are, first one is load performance is improved. Second one, the system efficiency is improved. Third, it prevents the output voltage from becoming negative. Choose the correct code for the given option. So here, as we already discussed, we know that the load performance is improved when freewheeling diode is connected in the circuit. It is right. And the second one, the system efficiency is improved. So obviously, when we are using the freewheeling diode, the current will be continuous, so that the power delivered to the load will be increasing. So when the output is increasing, automatically the efficiency is also going to increase. Okay, so that it is clear the system efficiency is improved. And third, it prevents the output voltage from becoming negative. So during the negative cycle, the freewheeling diode is taking care so that the negative voltage will not be applied across the load. If only the positive voltage, that is the current is supplied through this, so that the positive voltage will be available. Right? So all these three are true. So the option is C, 1, 2, and 3 are correct, right? So the answer is option C, 1, 2, and 3 are correct. And the next one here, a single phase 230 volts 1 kilowatt heater is connected across a single phase 230 volts 50 hertz supply through a diode as shown in the power figure. The power delivered to the heater element is. So here we are having only one diode, so it is rectifying. It is acting as the half wave rectifier, right? So only during the first off cycle, the power is delivered to this load. During the negative off cycle, it is zero. So from this, you can calculate the value of the voltage which is applied here, right? Which is applied and the current which is applied here, so that we can find out the power delivered to this load, right? The rating of the heater that is given as 1 kilowatt in this problem, and the supply voltage is given as 230 volts 50 hertz. From this, you have to calculate. So here you know that the RMS output voltage of the diode rectifier, half wave diode rectifier, is Vm by 2. As we already know this. So here Vm is equal to root 2 Vs, that is root 2 into 230 divided by 2. It will give the output RMS voltage. So here it is root 2 230 divided by 2. And the rating of the heater they are given as 1 kilowatt. Okay, 1 kilowatt. So from this you can find out the resistance of the heater, that is equal to 230 square by 1000. If it is the power, it is the power which is given here. So the resistance will be equal to V square by power. So power absorbed by heater element will be equal to V square by R, that is equal to 2 into 230 square divided by 4 into 1000 divided by 230 square. So here you will have this value, that is 230 square, 230 square will be cancelled and it is 1 by 2. So finally you will have 500 watts, that is 0.5 kilowatt. So the power absorbed by the heater will be 0.5 kilowatt. Right? So here the answer is 0.5 kilowatt, that is the answer A. Right? And we will go to the next one. A single phase full bridge diode rectifier. Single phase full bridge diode rectifier delivers a load current of 10 amperes, which is ripple free. The RMS and the average value of the diode currents are here. In this problem, they are given it is a single phase full bridge diode rectifier. Okay. So the load current they are given as 10 amperes. Load current they are given as 10 amperes. Okay. So for this, you have to calculate the RMS and the average value of the diode current. That is, what is the current which is flowing through the diode, we have to calculate. So here, the given value I naught is equal to 10 amperes. The RMS value of the diode current, we know that it is equal to, that is I naught square divided by 2, square root of I naught square by 2. That means I naught by root 2. So I naught is 10 and divided by root 2, it will give the 7.07 amperes. Is the value of RMS diode current as 7.07 amperes. And the average value of the diode current, we know that it is I naught by 2. Directly we know that it is I naught by 2, so it is 5 amperes. So here it is clear the RMS value of the output current is equal to 7.07 amperes and the average value is 5 amperes. So here the option D is the right one. So here for this, the option D is the right. Okay, next. The circuit shown below, the diode states at the extremely large negative value of the input voltage V1. That is V input VA, or the circuit shown below, the diode states at the extreme large negative value of the input voltage VIR. Here it is the circuit which is connected through two diodes. Okay. So for this, here, if the input voltage Vi of very large negative value, here the magnitude will be greater than the value of V. That is given here. This battery is greater than this value, and diode D1 will be forward biased. Okay, so the current will flow from the higher potential to lower potential. So automatically the current will flow through the diode D1 and it is forward biased, while D2 will be reverse biased and D2 will be reverse biased. Okay. D1 is on, D2 is off. Here the option D, right? And the next question, a single phase full bridge diode delivers a constant load current of 20 amperes. Constant load current of 20 amperes. The RMS and average value of the source current are here this 20 amperes and 20, because we know that this value of RMS output voltage, RMS output current and the average output current of the full wave diode rectifier is IRMS is equal to IS and the I average is equal to IS. So that here it is 20 amperes and 20 option B is right. And next question. A diode whose internal resistance is 20 ohms, I think it is volts, is to supply power to a 1 kilo ohm load from 230 volts source of the supply as shown in the figure. The percentage regulation from no load to given load is, here you know this input supply is 230 and the resistance load resistance is 1 kilo ohm and the diode internal resistance is 20 ohms. Okay, so you have to take care of this internal resistance, then only you can find the load regulation, right? So due to this diode internal resistance, there will be some small voltage drop across the diode. So we have to take care of this voltage drop. So here in this problem, the given values, that is the diode internal resistance is equal to 20 ohms and the load resistance is 1000, that is 1 kilo. At no load, load voltage will be is equal to Vm by pi, that is equal to 103.536 volts. And at given load, the load voltage is equal to, that is Vm by pi into R divided by R plus R naught. That is, we have to include this resistance, diode resistance. So 230 into root 2 by pi into 1000 by 1020. It will be 101.506 volts. And the percentage voltage regulation will be equal to V on minus V naught 1 divided by V on. So it is equal to 103.536 minus 101.506 divided by 103.536. So it becomes 1.96%. So here in this problem, the load regulation will be equal to 1.96%. So it is option C is the right answer. And in this question, they are given the assertion and the reason. The assertion given in this question is a single phase half-wave rectifier circuit is popularly known as one pulse rectifier. And why they are given the reason. A single phase half-wave rectifier circuit used to convert AC power to DC. Okay, so here we have to find the answer. So here the answer will be a single phase half-wave rectifier is popularly known as one pulse converter because of one cycle of supply voltage. That is one cycle of supply voltage, and there is one half cycle of output of load voltage. Hence, both the assertion and the reason are true, but reason is not the correct explanation for the assertion. If the reason is not true. So A is true, but R is false, right? In this question, they are given the assertion in three-phase converters, the ripple frequency of the converter output voltage is higher than single-phase converter. In three-phase converter, the ripple frequency of the converter output voltage is higher than in the single-phase. So it is the right one. We are already know. And the reason is the load current is mostly discontinuous in three-phase converter. Discontinuous, it is not the right one. Okay? So here you can see the answer. The load current is mostly continuous in three-phase converter, and the reason is false, right? So assertion is right, and A is true, and R is false, right? Answer C. The next question is assertion in a half-wave rectifier with RL load and with prevailing diode, the input volt ampere demand is less. In a half-wave rectifier with RL load and with prevailing diode, the input volt ampere demand is less. And the reason is with the prevailing diode, the stored energy in the load is itself. The stored energy is in the load itself. Both A and R are true, and R is the correct extension for the assertion, right? Okay, now we will move on to the controlled rectifier, right? Now we will move to controlled rectifier. So far we discussed only the uncontrolled rectifiers. Now we will move to controlled rectifier. So let us see the first question in this. In an SCR of the rectifier, the forward breakdown voltage of ACR is 110 volts. Forward breakdown voltage of ACR is 110 volts for a gate current of 1 milliampere. If a 50 hertz the sinusoidal voltage of 220 volts peak is applied, a time during which SCR remains on. If a 50 hertz sinusoidal voltage of 220 volts peak is applied, the time during which SCR remains off will be equal to, assume load resistance is 100 ohms and the holding current to be 0. So when it reaches 110 volts, we have to calculate. So here we know that V1 is equal to Vm sin theta. So here when this V1 is equal to 110 volts, the device will start conducting, right? So 110 it is equal to 220 into sin theta. That is sin theta will be 0.5, so that theta is equal to 30 degrees. Theta is equal to 30 degrees. So we know that the cycle, one cycle here the frequency is 50 hertz. So one cycle will be equal to 150. Okay, that is the time taken here. So here conduction angle, how long it is conducting is 180 minus theta, that is 150 degrees. It is conducting 150 degree, it is conducting. So it is equal to 2 pi into 50t is equal to pi by 6. Is equal to the time during which SCR remains off is 1 by, here 2 pi should come below here and 50. So 2 into 6 into 50, that is 1 by 600. Pi will get cancelled. So that we will have 1.67 milliseconds. So for the first 0 to 1.67 milliseconds, this device is in off condition. After that, it is turned on. And the remaining time, it will be in on condition, right? So here the answer is 1.67 milliseconds. That is the first one. Come to the next question. And an SCR full wave rectifier is connected across a sinusoidal voltage of 400 sin 314t. The RMS value of the current flowing through the device is 20 amperes. The power rating of SCR is equal to, that is, they are given the voltage and the current. From this, you have to find out the I square. So here it is, as the supply voltage is 400 sin 314t, Vm, we know that that is 400 volts. Peak inverse voltage will be equal to root 3 Vm in this problem. So here it is root 3 into 400, it is 692.8 volts. RMS value of the current is 20. Average value of the current will be equal to RMS value by form factor. We know that in this case it is 1.11, so it is 18 amperes. So the power rating of the SCR will be equal to peak inverse voltage into average. So it is 12.47 kilowatt. It is 12.47 kilowatt. Here it is 12.47 kilowatt is the power rating of the device. And first session, by using freewheeling diode, load performance becomes better. Freewheeling diode prevents the low voltage from becoming negative. These three already we discussed in the uncontrolled voltage. The same thing will be true for this also. So here, both A and R are correct, right? And R is the correct explanation for A. By using the freewheeling diode, load performance becomes better because load current uniformity is improved. Whenever load voltage tends to go negative, freewheeling comes into play, as a result of which load current is transferred from the main transistor to the freewheeling diode, allowing the thyristor to regain its forward blocking capability. Hence, both assertion and reason are the true, but reason is not the correct explanation for the assertion. The advantage of using a freewheeling diode with the bridge type AC to DC converter is there is improved input power factor. Power delivered to the load for the same firing angle is more when freewheeling diode is used as volt ampere input is almost the same, and with and without a freewheeling diode. Therefore, the input power factor with the use of freewheeling diode is improved. So when we are using the freewheeling diode, the input power factor is improved. A single phase full converter is connected at the strip terminals. Its average output voltage when firing angle is 30 degree is approximately equal to. Here we have to use the corresponding formula. So the V naught average is equal to 2 Vm by pi cos alpha. 2 Vm by pi cos alpha. So here it is given alpha is equal to 30 degree, Vm is equal to 430 into root 2. So that is V naught average will be equal to 2 into 230 root 2 by pi into cos 30. 30 degree, that is given in the column. So 230 into root 6 by pi, that is 179.33 volts. Okay. 179.33 volts. So it is roughly 179. It is the relevant answer. Okay, next question. SCRs with peak forward rating of 1 kV. SCRs with peak forward rating of 1 kV and average on-state current rating of 40 amperes is used in single phase midpoint converter. If the factor of safety is 2.5, then the power that this converter can handle is you have to find the power. So the maximum voltage across SCR and single phase midpoint converter is 2 VM. It is 2 VM. Therefore, the converter can be designed for a maximum voltage of 1000 divided by 2 into 2.5, that is 200 volts. Is 200 volts. The maximum average power that the midpoint converter can handle is, that is the P average maximum is equal to 2 Vm by 5 cos alpha IT average. For maximum, cos alpha will be equal to 1. So it is 2 into 200 divided by 5 into 40 into 1 by 1000 kilowatt. So finally, you will have 16 by 5 kilowatt. 16 by 5 kilowatt. The first answer is the right. Okay, next one. The main advantage of a dual converter with circulating current operation is first one, the efficiency and the power factor are more. And second one, it has faster operation than dual converter without the circulating current. So the resistors are rated for lower current. Here, the answer will be here when circulating current gives rise to more losses in the converter. Okay. When there is no circulating current, the loss will be reduced. Hence, the efficiency and power factor are low. The statement 1 is false. In a non-circulating current type dual converter, the normal delay period of 10 to 20 milliseconds is required, while no delay period is required in circulating current type dual converter. Therefore, circulating current type dual converter is faster than non-circulating type dual converter. Thus, statement 2 is true. So, statement 1 is false and statement 2 is true. And you have to inspect the third one. As the dual converter, its circulating current has to handle load current as well as circulating currents. Therefore, the thyristors are rated for higher currents. Hence, statement 3 is false. So, 1 is false, 2 is true, 3rd is false. So, choose the correct code for the one. And only 2 is true. So, option C is the right. Yeah, 4-quadrant operation requires. They are given the option 2 full converters connected back to back. 4-quadrant operation. We already know this. And 2 full converters in series, 2 semi-converters connected back to back, 2 full converters connected in parallel. So the option is A. Right? In case 4-quadrant operation is required without any mechanical change of switch, 2 full converters can be connected back to back to the load circuit. Such an arrangement using 2 converters in anti-parallel connected to the same DC load is called dual converter. Consider the following statement associated with single phase midpoint converter configuration is used in case the terminals on DC side have to be grounded. And second one, the transformer rating in midpoint converter is double the load rating. And third one, the SCRs are subjected to peak inverse voltage of 2 Vm in single phase midpoint converter. Fourth one, which converter is preferred for midpoint converter? Which of these statements are correct? We will inspect these statements. In midpoint converter, each secondary should be able to supply the load power. In midpoint converter, each secondary should be able to supply the load power. Due to this reason, the transformer rating in midpoint converter is double the load rating. Thus, statement 2 is not correct. The remaining things will be correct. Right? Except 2. Which of these statements are correct except 2? So here this first option, that is 1, 3, 4 are right. Option 1 is the right answer. And next question 10. Here they are given the assertion the computation overlap is more predominant in semiconductors than in full converters. Computation overlap is more predominant in semiconductors than in full converters. Reason the computation varied in seconds when outgoing and incoming SCRs are conducting is known as overlap period, right? So here we know that the computation overlap is more predominant in full converter than in semiconductor. Hence, the assertion is false. Assertion is a false. For a single phase full converter having a full load current of I0, match the list 1 or overlap angle with the list 2 output voltage and select the correct answer using the codes given below the list. L is the source emitters. In the list 1, they are given the overlap angle mu is equal to 0 degree, and in the list they are given for mu equal to 0, what is the expression, and for mu is equal to 180 degree, what is the value, and for the value of overlap angle from 0 to 180 degree, what is the value, we have to find out. Okay, so now we'll see this expression. So when there is a value, there is overlap angle is from 0 to 180 degree, you are having the expression that is 2 dm by pi cos alpha minus omega ns by pi I naught. So here for u is less than 180 degree, you are having this expression. And when it is equal to 180 degree, this value will be equal to 0. And for overlap angle is 0, it becomes 2 dm by pi cos alpha. Is 2 dm by pi cos alpha. So for 0, you are having 2 dm by pi cos alpha. So for A, it is answer is 3, right? Answer is 3. And for B, for 180 degree, it is equal to 0. So it is 2. And for overlap angle less than 180 degree, it is 2 dm by pi cos alpha minus omega ls by pi I naught. This 1. So 3, 2, 1 is the right answer. So here you can see the option D. So option C, 3, 2, 1. So option C is the right one. The next one. Which of the following converters can feed power in any of the 4 quadrants? This 4 quadrant converter we have to know. First one, full converter. We know that it is a 2 quadrant converter. And second one is the dual converter. It is a 4 quadrant converter, as we know. And C, semiconductor, it is a single quadrant converter. Combination of semi and full converter. Generally, we are not using this. So here, dual converter is the 4 quadrant converter. So a dual converter using 2 full converters can do 4 quadrant operation as well. Okay, consider the following statements. In a full converter, direction of current cannot reverse. In semiconductors or single quadrant converter, that is, in a full converter, direction of current cannot reverse. That is, output voltage may be positive or negative. It is a true one. Semiconductors or single quadrant converters, so we know that voltage and current is always positive. The full converter can operate as a 2 quadrant converter. Since the voltage is positive or negative, so it can be operated in the 2 quadrants. The full converter operates as a rectifier in the first quadrant and as an inverter in the second quadrant. Okay, we know that when the alpha value is greater than 90 degree, it will act as the inverter. That is, it is the inversion. Power flow will be from the load to supply. Like this, we can use the full converter, right? In a full converter, direction of the current cannot reverse, but polarity of the output voltage can be reversed. Okay, this is the right. So, each of the statements used above are correct. We have to write. So here you can see this. A full converter operates as a rectifier in the first quadrant, and from 90 and as inverter in the second quadrant, right? Fourth quadrant. The statement 4 is not correct. So here it is operated in the fourth quadrant, not in the second quadrant. Okay. So in this option 4, they are given as second quadrant. This, if it is the fourth quadrant, it is also right. So option A, 1, 2, 3, and 5 are correct. A single word, a second. If it is given as 4, all 5 are true. Right? So you have to clearly see this. Next question. AC to DC circulating current wave converters are operated with which of the following relation between their triggering angles alpha 1 and alpha 2? So we know that it is alpha 1 plus alpha 2 is equal to 180. In the answer, D is the right. In AC to DC circulating current, the firing pulses of the converter are also adjusted that alpha 1 plus alpha 2 is equal to 90 degrees. A single phase half wave, a single phase half wave controlled converter with a resistive load is operated from a 120 volts 50 hertz supply. If the average output voltage is 28% of the maximum possible output voltage, the firing angle the thyristor would be equal to. Here you have to calculate using the average output voltage expression, right? So here the average output voltage expression is dm by 2 pi into 1 plus cos alpha. So if alpha is equal to 0, you will have the maximum output voltage. In this 25%, for this we have to calculate the value of alpha, okay? So according to the question, V naught is 25% of V naught max. So we know that V naught max is dm by pi. In this 25%, it is 1/4 of dm. So when you are equating and finding the value of alpha, dm by pi will be cancelled, 2 and 4, it is 1 by 2. And cos alpha becomes minus half, and alpha will be equal to 120 degrees. So in this, the answer is they are not given any 120 degree, none of these. A single phase full controlled thyristor bridge converter supplies the load consisting of RLE as shown in the figure. The inductance L in the circuit is so large that the output current may be considered to be virtually constant. The firing angle alpha is, you have to find it. Okay? So it is RLE load. So for this, you have to use the corresponding expression. So for a single phase fully controlled thyristor bridge converter with RLE load, the average output voltage is 2 Vm by pi cos alpha, that is equal to 2 into root 2 into 220 by pi cos alpha. This 198 cos alpha. Now, VDC minus IDC is equal to IDC R plus E. That is equal to 10 into 0.5. 10, the current is already given. So resistance is 0.5, it is plus 135. So VDC is equal to 140. By equating these two values, 198 cos alpha is equal to 140. So cos alpha is equal to 140 divided by 198, that is equal to 0.707. And finally, you will have the value of alpha is equal to 45 degrees. 45. The answer in this is equal to, this option B is equal to 45 degrees. Consider the following statements. First one, fully controlled or the half controlled circuits both are capable of regeneration. Fully controlled and half controlled circuits both are capable of regeneration. So we know that during the regeneration, the current should flow from the load to source. Actually, in half controlled converter, the current cannot flow from the load to source. So regeneration is not possible. But in case of fully controlled converter, the current can flow from the load to the supply so that regeneration is possible. And the second, the higher the pulse number, the lower the magnitude of the ripple voltage and current in the load circuit and the AC supply. So when the pulse number is increasing, the ripple voltage, frequency of the ripple voltage is also increasing. And the lower order harmonics is eliminated depends upon the pulse number. So this statement is true. And third, the bridge circuits and half the circuits both require same number of resistors to carry the same current. Actually, the bridge circuit and the center tap type. The center tap type is having two resistors, but the bridge converter is having four resistors. Okay. So here in this bridge type circuits, it requires more number of devices compared with the other configurations. So it is not the right one. And fourth one, all these circuits tend to be used for low voltage, high current use. Which of the statement given above are not correct? Okay. Half-wave circuits, usually the current is discontinuous. Generally, it is not used for high current operation. So here we have to find which statements are not correct. So we know that the fourth one is not correct and third one is not correct. And second one is the right one. First one is not correct. So one, three here. So here, one is not correct, two is correct, and three is not correct, and four is correct. Okay? So here not correct, one and three are not correct. One and three are not correct. And next question. In a three-phase bridge converter, the DC load current is 90 amperes. The competitive inductance per phase is 50, and the three-phase power supply is 2.3 kV. The reduction in output voltage due to overlap is around. Here we have to use the corresponding expression, that is 3 omega ls by pi IDC. So this they are given a frequency and all. So 3 omega is 2 pi f, that is 2 pi into 50, and ls is 50 microhenry, that is 50 into 10 power minus 6 divided by 5 into 90 IDC. They are given. So it becomes 1.3735 volts. So and option B is the right answer. The holding current of SCR in three-phase full converter is 200 milliamperes and the delay time is 2.5 picosecond. Converter is supplied from a star connected 208 volts 30 hertz supply. Has a load of R is equal to 2 ohms, L is equal to 8 milliamperes, and the firing angle is 60 degrees. The minimum width of the gate pulse PP for L is equal to 0 MPes. That is, here we have to find out the minimum pulse width of the gate pulse, right? So they are given the delay time and the holding current and the resistance and inductance values. From this we have to calculate. Okay. So here holding current is 0.2 amperes and time delay is 2.5 microsecond. Alpha is equal to 60 degrees. Actually, it is a microsecond. Okay. So it is microseconds and alpha is 60 degrees and R is equal to 2 volts. And Vs equal to 208 volts and frequency is 50 hertz and L is equal to 0. Phase voltage Vs is equal to 208 by 2, that is 130 volts. And peak voltage is equal to 42 into this Vs phase, that is 169.7 volts. And this given us root 3 Vs maximum into sine omega t plus 30 degree. At omega t is equal to 60 into and E is equal to root 3 into 169.7 into sine 90. That is equal to 293.93 volts. The rate of rise of anode current, dA by dt at the instant of triggering is dA by dt is equal to E by L, that is 29.0, that is infinite. So the time gate pulse with the required T is equal to IH by dA by dt is 0.2 divided by infinity, that is equal to 0 microseconds. So minimum pulse width of the gate pulse is that pulse width is equal to T plus TD, that is 0.25. That is the delay time. Okay. So it is 2.5 microseconds. That is the minimum pulse width required to turn on the device. The nature of load current, that is whether load is continuous or discontinuous, is in controlled rectifier is depends upon only on the type of load. Second, does not depend upon type of load and firing angle delay. And third, depends only on the firing angle delay. Depends on both the type of load and the firing angle. Okay, here in both the conditions we have to check. The term continuous means that load current never causes cases but continues to flow through SCR or their combination. The term discontinuous is applied to the condition when load current reaches zero during each half cycle before the next SCR sequence is fired. In practice, the output current may become discontinuous at high values of firing angle or at low values of load current. In a three-phase cell converter, the output voltage during overlap is equal to, that is equal to 0, right? Output voltage with no overlap is equal to internal voltage of the three-phase cell converter, that is 3 VLM by pi cos alpha. So here it is the expression for the output voltage. So here the peak inverse voltage in AC to DC converter system is highest in that is peak inverse voltage of three-phase bridge converter is root 3 VM, that is 1.732 VM. Peak inverse voltage of three-phase half-wave converter, that is equal to root 3 VM is equal to 1.732 VM. Peak inverse voltage of single-phase full-wave midpoint converter is minus 2 VM, that is the highest one. And peak inverse voltage of single-phase converter will be equal to minus. So in this peak inverse is highest in single-phase midpoint converter. Single-phase midpoint converter. That is minus 2 VM. A transformer is having source voltage of 400 volts and turns ratio of 2:1. The transformer is centered up if the secondary is connected to single-phase full-wave converter. Peak inverse voltage of SCR will be equal to, so here it is equal to 400 into 1 by 2, that is 200 volts. The peak inverse voltage will be equal to 200 into root 2, 200 into root 2. That is the option A is the